whenever you're ready, or you can eat if you want.
No.
Brian's going to talk to us about proof theory applied to automated theorem proving.
All right, thanks. Does anyone feel like getting their hands dirty? Okay. This is going to be a somewhat interactive talk, not really, but anyone else want to get their hands dirty? I'm not going to ask you any questions, but if you want to get your hands dirty, then let's play a game. And so this game is going to illustrate some basic principles of proof theory. It's called the MIU Formal System. Here's some recommended reading, and here's what we're going to talk about.
I noticed that you had a date in the future you recommended reading.
Yeah, I'm giving myself 5 years to publish that. So some of this talk is based on my research. Some of it's based on these other books. I do highly recommend this one, Gödel, Escher, and Bach, An Eternal Golden Braid. That's a book that's about simultaneously music, that's the Bach, math, that's the Gödel, who's, some people cite him as one of the top mathematicians of the 20th century. I don't think that's the total ordering, so I'm not sure if you can compare mathematicians. But anyway, Escher, is the artist. So this book is on the subject that combines those three areas and gives some common themes. And the common theme will be what's called a formal system. Okay. So I do recommend reading Gödel, Escher, and Bach. This MIU Formal System, it's a game sort of to illustrate what proof theory is about. So the MIU Formal System was developed by Hofstadter, the author of Gödel, Escher, and Bach. So I'm going to completely steal his ideas and show you the game, and just to illustrate proof theory, what's going on. So at first it's going to seem, and this is where you're going to get your hands dirty, it's going to seem completely meaningless, and that's on purpose, because this is all about syntax. There's no semantics involved yet. So ultimately what we're trying to do is get computers to prove things. Okay? So that's ultimately what we're trying to do. In maybe 1,000 years, we want to give it the Riemann hypothesis, and it spits out 200 terabytes that proves, something like that. That's the goal. The question is how to go about that. And I don't know if it's realistic to expect that to happen in my grandkids' lifetimes, but that is one of the ultimate goals of proof theory. I also want to talk about how this proof theory is all under the umbrella of something called metalogic. Metalogic is logic about logic, so I'll explain what that means. And all digital computers are isomorphic to formal systems. So there's a dictionary between all formal systems and all digital computers or programs. So if you're interested in computer science and learning more about digital computers and programming, formal systems is the abstract correlation of that. So we'll talk about that connection really briefly. So so here's a game, okay, and this is a game kind of like chess, where there's a starting position and then there are movement rules. And the question, I'll ask the question after I state the game. So you start with a string mi. Okay. And remember, this is syntax, so that's supposed to be completely meaningless. Now, it actually has a meaning, but it's more fun if I don't tell you what it means. So here's the rules. There's 4 rules. So let S and T be strings. And a string is just a, in this case, finite sequence of symbols. Here's the rules. If you have a string ending in I, then you can tack on a U. So the alphabet is just 3 symbols, M, I, U. So there's basically 3 pieces in this game. So it's a lot simpler than chess. And let's see what else. If you have a sequence or a string like this, then you can double the string. The third rule is if you have 3 I's in a row, you can change that to S-U-T. Okay. I'll give some examples. And fourth rule is, and this is my favorite rule, if you have 2 U's in a row, they completely go away. And so I'll leave these on the board for those of you who are getting your hands dirty, because to play this game you might need to see the rules. So actually what I'll do is do that, yeah. So I can erase this. Oh, I'm already telling you some of the meanings of these things. MI is what we're going to call an axiom. I'm kind of spoiling the whole drama here that's unfolding. But anyway, the question is, I'm gonna give you, there's 2 types of strings. Type B will be not A. And a type A string is one that is obtainable with these rules. So, obtainable within rules. Okay? So if this were chess, we're kind of like asking, is it possible that on the chessboard you have 2 knights and that's it? Is that possible? No, it's not, because there's always 2 kings on the board. So that's not possible. The question is, categorize the string MU. Which one is it in? Okay, so, and prove your assertion. Okay. This is the very spirit of proof theory. And then what we're going to talk about after I kind of mention how to solve this riddle is how all this abstract nonsense applies to computing and getting computers to prove things. Basically, what we're going to be able to do is say that there are computers that can answer this question. Okay. Now, I'm going to reveal for you now that type A things are going to be called theorems. But I like to call it type A because theorem is a human notion. Okay? Theorem is a human notion. So, and then type B is just not theorem. I'm not saying it's a false statement, but just not a theorem. An example is the continuum hypothesis. That's not a theorem in ZFC set theory. The continuum hypothesis has been proven to be completely independent of the usual axioms. So this is actually kind of like that. Well, I already spoiled it for you. Turns out that MU is not obtainable from these 4 rules. Try as you might, you will never get MU as a string. So what that means is that MU is not a theorem. And the way you prove that, there's something called induction on formal systems. This induction principle, actually, I found out that this is true for all formal languages. A formal language is something that abstracts formal systems. And this induction principle is apparent in everything that's recursive in nature. everything recursive in nature admits an induction principle. And this is certainly a recursive type system because you can iterate these rules and, let me just give like a concrete example. So you can start with MI, that's your initial state as your input for a program. Did you get your hands dirty at all?
Yeah.
Can you tell me a string that is a theorem?
M, I.
Yep, that's a theorem. Does everyone see that? That is a theorem in this system. You can apply one of these rules, well, several of these rules in a row, right? And then you can obtain this. So this is a theorem. Okay. So the question is MU a theorem? That's not entirely fun to figure out. It's actually not. And the induction principle is this. The thing you can notice is that the number of i's is never divisible by 3. You could prove that by induction. And then if there's no i's, that's not possible because 3 divides 0. Yeah. And so this is not possible, and you could prove that with an induction principle. That induction principle applies to all formal languages, not just formal systems. So a theorem is something that is basically a legal move in this game. What proof theory is about, okay, like in geometry the objects of study are points, lines, planes, circles, things like that, and various combinations of that. In proof theory, the objects are proofs and theorems and axioms. How do you prove the continuum hypothesis is independent of the other axioms? Well, it's basically a similar idea. So in set theory, to give a more relevant example, and by the way, this means intelligent mode, and this means Zen mode. So I don't know what that means, but that's what Douglas Hofstadter was inspired by. Anyway.
I think it's in Korean, right?
I don't know. Yeah, mu. Yeah, mu or mu. Yeah, mu is. I don't know what that means. Nobody knows what it means. I don't think. But it basically, if you ask a question and the answer is mu, that means bad question or something like that. It means your teacher will slap you on the head with a sandal. So Zen mode is not obtainable from either intelligent mode or machine mode. That's the basic idea. But why it relates to that, I don't know. But that's what Hofstadter thought. Anyway, so let's take a moment. Let's take a peek at set theory. I'm actually not a set theorist. I'm not interested in researching set theory. I just want to exploit it, for computer science purposes. In set theory, it's a little bit more complicated because you have more axioms, but that doesn't necessarily complicate things. When you add more axioms, if they contradict each other, then you have no theorems. Or actually, no, you would have every statement is a theorem, which is lame. So in set theory, we have two inputs, sets that kind of exist for no apparent reason, and then natural numbers. So the inputs are empty set and natural numbers, and then there's like 6 rules for forming new sets. And I'm going to call that a program because this is a program, and like one of them is if you have x and y, then you can pair them up and call that a set. So this is very similar to the MIU system, okay? So that's why I did that easy one first, is because set theory is just like that. You have 2 inputs and you have like 6 axioms, and that's some people think that that's enough to generate all math, but it doesn't have anything to do with category theory or any of that, or formal languages. I'm going to explain what this picture is if I have enough time, which I doubt I will, but maybe I'll try to remember that. And So is MU a theorem? No. So a proof, you know, I have to define a proof in a proof theory talk. A proof is basically a derivation. So you start with MI. I'm going to write for you a proof in the MIU system of this type A statement. I think there's only like one way to get that. You can use the doubling rule twice. So, or no, the tacking on of the I rule. If it ends in I, no, it's the doubling, you use the doubling rule, right?
Yeah.
Okay, and then you double that. Yeah, you notice, let me actually show you a nifty picture. So there's graph theory in here. I was a little annoyed when I made this because I did this kind of manually, and then I found out that there's actually someone wrote a program to do it, and kind of it was annoying because I had to color each edge and all that. But anyway, here's the picture. I think my picture's a little bit better anyway. You can, I don't know if you can read that, but MI is this string right here. Every vertex corresponds to a string. Okay. So this is your input is MI. Now there's two rules. You can apply the doubling rule to get MII, and then I know it's hard to read, but here's your MIIII. So if there is a path, then that is a theorem. And what's tricky about this graph is you can always double the string. So it's actually an infinite graph. So that kind of complicates things. You can't really do an adjacency matrix with that. And this is a directed graph, so you can't go backwards. You can't do a reverse logic. That would be a non sequitur fallacy. If you can't, or that would be assuming converse is always true. And we all know converse is not always true if the original is true. So you can't necessarily go back, but you know, some interesting things happen, I think. You're starting at MI, you can go here, that's a theorem. You can go here, so that's a theorem. Let's see, where else can you go? Down here, so this is a theorem. Up here, that's a theorem. Up here, and then you get back to MI. So you can actually prove that if A is true, then A is true, which is not very helpful. But I always get excited when I can use the black rule because you can, like most of these rules add characters to the string, and we want to get to MU. Okay, so we don't really want to add a bunch of characters, we want to take away characters. But the key idea there with a takeaway is that there, in all recursive systems of any kind in formal language theory, there's always an induction principle, and that allows you to make statements about theorems in their totality. Like you can say, this can't be a theorem, and that's just like the continuum hypothesis. From set theory alone, you can't prove it. And it's something like this, I would imagine. I can't pretend to understand that proof, but it's along these lines. And yeah, so yeah, if there's a path, then there's a proof. Now, when we're talking about making computers find these paths, you know, in other words, find a proof, MU might be on the moon. Okay? You might have a statement that's not on the graph, and MU is one such statement. It's not on the graph, but how do you prove that with a computer? Well, a computer can actually do that because you can formalize induction. Okay? You can formalize induction. All induction proofs basically work the same way. A computer can do that too. So we want to come up with an algorithm of some kind, like the Riesz algorithm for integrals, where it'll spit out not theorem, or it'll spit out proof of theorem. And the proof of theorem, like if you input Riemann hypothesis or P versus NP, which of course no computer can do right now. I don't know, maybe DeepMind could figure it out, but well, probably not because it's a Go computer. So yeah, let's go on. We talked about the comparison between proof theory and geometry. Okay, so in proof theory, the objects of study, like I said, are alphabets, utterances are strings. Well-formed formulas, a well-formed formula is basically a legit string. Like for example, you could use formal language induction to prove that there is no formula with an odd number of parentheses. They always come in pairs. I know that seems kind of trivial, and it is. I'm not doing anything like super deep yet. But yeah, you can use induction to prove that for all well-formed formulas, you can't have an odd number of parentheses. I remember on my final once that was a question, is prove that for all woofs, they're called woofs, that the number of parentheses is even for all such formulas. Axioms, which are the inputs of the program, the rules, blah, blah, blah. So those are the objects of study. So the alphabet of a formal system is just a set. Now you won't see that anywhere else except, well, I've never seen it anywhere, but they always require that the set of symbols like MIU, they always require it to be countably infinite. But I've never found a particular reason why it has to be limited to countably infinite. So S is any set. We're going to say that that set consists of symbols. Like if you have the set containing A, B, C, those are all symbols. Okay? So any set we're going to allow to be an alphabet. Those are like your chess pieces. Knight is in the alphabet. Queen is in the alphabet. And then a grammar is the set of all well-formed formulas. The grammar is the collection of all the legit utterances. Like there's a lot of utterances, like saying calculus, or analysis, I should say. We want to see, is it possible to prove that something is not a theorem in analysis, or number theory, something like that. So like in calculus, there's a difference between an utterance versus a woof, okay? Well-formed formula. An utterance would be like, let's see, it's hard for me to say something that doesn't make sense. No, I don't know if that makes no sense, but this is well-formed expression. Okay. This one's not, or if I just write, there's an easier example, plus. Although that could mean a set of ordered pairs. But just by itself, if you were to ask anyone on the street, they'd probably tell you plus by itself is not it's not grammatically correct. Normally we would write A plus B, and that's no longer an utterance. That actually that's a legit grammatically correct formula. Okay, so there's that. Axioms, we talk about axioms. The thing about logic though is that, well, in comparison, the MIU system has one axiom. In logic, there's infinitely many axioms, which kind of complicates that graph. That graph has infinitely many starting points, and the nice thing about logic though is there's only one rule. Only one rule. So you have this kind of notion where you're either going to have a short list of axioms and lots of rules of inference, or you're going to have one rule of inference and lots of axioms. And the precise statement of that is what I call the trading theorem. I don't know it, so you can trade a rule of inference for an axiom, and the systems prove the same theorems. Not just isomorphic, but the theorems are identical. I don't know, I really doubt I was the first one to do that, but I couldn't find it anywhere in the literature. And anyway, I'm not going to go through all these axioms because, you know, it's about as interesting as MI. And, you know, but this is how we can, if we can program this into a computer, then a computer can theoretically apply the same basic ideas of the MIU system to prove actual theorems that we're actually interested in. So every tautology is an axiom, for example. So A implies A is a tautology. That means A implies A is always true. We're taking that as an axiom. And you can, it's kind of out of focus. Oh, and just for the YouTube watchers, I copied this from Anderton's book, just so it doesn't look like I'm plagiarizing. Alpha is a well-formed formula. If you have the well-formed formula, in some cases you can tack on for all x. Okay, and that's still, well, we're going to take that as an axiom actually. Anyway, those are the rules. It's not really important right now. Here is the isomorphism between digital computers and formal systems. We don't need that, do we? There we go. Okay. So there's two rows in this table. This is the isomorphism that maps formal systems to digital computing. We're talking about programs, and this is not digital computer, not at all abstract. You know, Siri basically uses formal language theory to always produce a grammatically correct statement. You'll never hear Siri say something grammatically incorrect. Well, in theory. You could probably prove that, you know, he or she or it will never produce nonsense. The ideas in there are in automated theorem proving somewhere in formal language theory. Because we want Siri to always say something grammatically correct. Otherwise, we're talking to an assembly coded machine. And anyway, the alphabet is, in a formal system, it's the set of symbols that we're going to use. In digital computers, we typically use binary, so it's just 0 and 1. The RISC chip could do 3 values. I don't know if that was any better for anything, probably for fuzzy logic problems. The grammar consists of 8 characters out of the alphabet. That's called a byte, so the grammar, it's grammatically correct if it's 8 characters. The axioms are the input of a program. The rules of inference are the program, and yeah, I don't have to read everything off, you can read. So there is an isomorphism there. So whatever you discover about formal systems, you can apply that to the theory of computer science. This is math talk, so I should have some math on the board. This is the general form for rule of inference. So something is a rule of inference if it looks like this, or if this is true. So U of A is the set of all utterances, legal or not, well-formed or not. You take n of those in a certain order, and if a rule of inference has to take n inputs and produce something. If it ends in I, you can tack on a U. That's the general form of a rule of inference. The arity of the rule tells you how many inputs it takes in, and basically for the MIU system, the arity is always 1. There's always 1 input. Now for logic, there's going to be 2 inputs. It'll take 2 formulas, and you'll be able to conclude a consequence from that, which I will mention in a second. So the only rule of inference is what's called modus ponens. I don't really know what that means except mode of something. I would assume. That rule of inference says if you know phi is true and if you know that phi implies beta, the rule of inference says you can conclude beta, which is like a really simple fact. But which is good. So when you're doing induction proofs, trying to prove something about all sets, like all sets can be well ordered, or the Cantor-Schroeder-Bernstein theorem, something like that. I mean, if you wanted to use induction, which would probably not be that smart, but there's one rule of inference which makes all the induction proofs really simple. Basically, the induction principle, it goes like this. Okay, so let W be all the grammatically correct utterances, okay, and let, what's a good letter, not R, phi, or beta, let's let P be a subset of W. So P is just a collection of woofs. And what I'd like to do is prove that some property holds for all woofs, just like normal induction. You're trying to prove something happens for all natural numbers. And this principle is a generalization of that, actually. That's a corollary to the theorem I'm about to write down. If the following is true, then that thing is true for all formulas. Okay. So first of all, it has to be true of the atomic formulas. So atomic formulas is a subset of P. And the other thing is it has to be closed under all the rules. And what's nice in logic is there's only one rule. So we only have to show closure in one instance. But we have infinitely many axioms to check. So either way, proving something about all sets, like all sets can be well ordered, by induction would not necessarily be smart. But it's nice to know it's there in case you want to prove continuum hypothesis independent of the other axioms. So closure under rules, all rules. And in logic, there's only one rule, that. And we are abusing the notation because technically R should be inputting strings. Phi is not a string. It represents a formula, so we technically need to put quotes around here and here and here, but I'm just kind of ignoring that for right now. When you need to program this into a computer, that does become important, although at this point it's probably not very instructive. So if you want to get your hands dirty or your brain dirty, sounds bad. Proof assistant is something that can check a proof or determine if something is true or false. Mathematica serves as a proof assistant. I'll tell you that one of these is going to come out true and one of them is going to come out false. And I want you to think about which is which. And Mathematica can do it like that. But as my professor, who's may he rest in peace, David Meredith, he said, Mathematica is very dumb but very fast. So the speed kind of makes up for how dumb it is. But it's very fast and has good programming. So anyway, the first one, reduce, is asking Mathematica to tell you if it's true, false, or it can't determine. Often reduce will just say not able to assist with this proof. What this says is there exists a y such that for all x, x plus y equals 0 among integers. Now I want you to think about that and then contrast that with the quantifiers reversed. And one of these is true and one of these is false. Spoiler alert, the first one's false, according to Mathematica, and the second one's true. This is a proof assistant. Okay? Proof assistant will not give you a proof, but it will tell you basically, yes, it's a theorem, or its negation is a theorem. But no proof is given. And so, it would be cool if on one hand, if we could put in Riemann hypothesis and it said true or false. What we want is a proof. So that's where automated theorem proving comes in. These actually find proofs. Now, these proofs are not guaranteed to be readable by a human. They're basically assembly code. Formal, very formal proofs with strings that are like super long and impossible for a human to understand. But it might be nice to know something's true before you try to prove it. Like, it would be nice for it to tell you, and actually I've seen on Wolfram Alpha, it's now saying Riemann's true. So apparently Stephen Wolfram came up with some way to check it, although there's still no proof. The proof for Riemann might be a, petabyte of data, I don't know. But anyway, this is a graph theory question. Is there a path between two vertices on a directed colored graph that's infinite in size? Where there's certain generation rules for what gets a path and what doesn't. So this is why it's hard. For example, suppose you're making Google Maps or something and you tell it, okay, you're actually not going to give it the complete map. All right? You say, I want to start at San Francisco and I want to end up at something I'm calling LA. How do I get there? So if you can find a path, then you've found a proof. But the problem is, your thing that you want to prove might be Paris. Okay, it might be Paris. There's no path to Paris. How do you get a computer to decide there is a path or it's in a different country and there's no path? So I don't know enough graph theory to answer that question. The adjacency matrix is infinite. I don't know, maybe it has to do with random walks or something, but I don't know enough graph theory to do that. And there's the pretty picture again. Let's see, is there anything I missed? Oh yeah, so this thing. In conclusion, does anyone recognize that or can classify that type of image? I know the coloring is a little bit off. This is white on blue. Any ideas, conjectures for what this is, what type of picture this is? It's not a fractal.
Is it a gravity graph?
It is a complete graph with 30 vertices. But what type of document is this? Hint, architecture. Blue background, white foreground. Any guesses what type of document this is? These are blueprints. Okay? People who study foundations think that they're finding the blueprints of mathematics. That's what they think they're doing. They think they're finding the blueprints for all of math. These are not the blueprints of math. However, I do have the blueprints of math somewhere. I don't know. Well, anyway, these are the blueprints for math. They've already been found. Now the question is, can you build something from the blueprints? And if you can't, it's not a theorem. That's the basic idea. Now, are there any questions?